When terminating THHN wire on a standard QO breaker, you should size the wire based on the 75°C column. This is because QO breakers are typically rated for a 75°C temperature rise. This means the breaker can safely operate in an ambient temperature up to 40°C without exceeding its maximum allowable operating temperature of 75°C. THHN wire itself is rated for a maximum conductor temperature of 90°C. However, when using THHN wire with QO breakers, the ambient temperature must be considered. If the ambient temperature is 40°C or less, you could technically size the THHN wire to the 90°C column. However, if the ambient temperature exceeds 40°C, you must size the THHN wire to the 75°C column. This ensures the breaker does not exceed its maximum allowable operating temperature. Therefore, it is safer and more conservative practice to always size THHN wire to the 75°C column when terminating on a standard QO breaker. This approach ensures you stay within the temperature limits of the breaker, regardless of the ambient temperature variations. Following this practice will help to ensure safe and reliable electrical installation. It is important to consult the National Electrical Code or NEC for specific wire ampacity tables and requirements related to conductor temperature ratings and termination limitations. Correct wire sizing is crucial for preventing overheating, insulation damage, and potential fire hazards. By adhering to the 75°C rule for QO breakers, you are providing an additional safety margin. Always prioritize safety and consult relevant electrical codes and standards when making wiring decisions. When selecting wire sizes for electrical installations, it's crucial to consider several factors beyond just the breaker rating. Firstly, the ampacity of the wire, which is its current carrying capacity, must be sufficient for the intended load. This ampacity is determined by the wire gauge and its insulation type, such as THHN. Secondly, the temperature rating of the terminations, including the breaker and any other connection points, plays a vital role. Devices like breakers are designed to operate within specific temperature ranges, and exceeding these limits can lead to malfunction or failure. Thirdly, the ambient temperature in the installation environment must be taken into account. Higher ambient temperatures can reduce the wire's ability to dissipate heat, which in turn lowers its ampacity. The NEC provides tables and guidelines to help you determine the appropriate wire size based on these factors. For example, NEC Table 310.15 B16 lists the allowable ampacities of insulated conductors rated up to 2000 volts, 60°C through 90°C in free air based on an ambient temperature of 30°C. If the ambient temperature is higher than 30°C, correction factors must be applied to reduce the allowable ampacity. NEC Section 110.14 C1 specifies that terminations for circuits rated 100 amps or less, or marked for conductors size 14 AWG through 1 AWG, shall be used with conductors rated for 60°C or 75°C. This means that you must select a wire size based on the 60°C or 75°C column in the ampacity table, unless the equipment is specifically listed and marked for use with 75°C or 90°C conductors. QO breakers typically fall under this category and are generally rated for 75°C terminations. Even though THHN wire is rated for 90°C, the termination temperature rating of the breaker governs the wire sizing in this case. Ignoring this requirement can lead to overheating at the termination point, potentially causing damage to the breaker and creating a fire hazard. It is always best to err on the side of caution and use the 75°C column for sizing THHN wire when connecting to standard QO breakers. This approach ensures compliance with the NEC and promotes a safe and reliable electrical system. Also, it is a good idea to consult with a qualified electrician or electrical engineer if you are unsure about any aspect of wire sizing or electrical installation. They can provide guidance specific to your application and ensure that all work is performed in accordance with applicable codes and standards. When dealing with electrical installations, it's crucial to understand the concept of derating. Derating is the process of reducing the allowable ampacity of a conductor based on various factors such as ambient temperature, the number of current carrying conductors in a raceway, and the presence of harmonics. One common reason for derating is high ambient temperature. As mentioned earlier, the ampacity tables in the NEC are based on a specific ambient temperature, typically 30 degrees Celsius. If the actual ambient temperature exceeds this value, the wire's ability to dissipate heat is reduced, and its ampacity must be derated accordingly. Correction factors for ambient temperature are provided in NEC Table 310.15. B2. For example, if you are using THHN wire rated for 90 degrees Celsius in an ambient temperature of 50 degrees Celsius, the correction factor would be 0.82. This means that you must multiply the allowable ampacity of the wire by 0.82 to determine its derated ampacity. Another reason for derating is the presence of multiple current carrying conductors in a raceway. When multiple conductors are bundled together, they generate more heat than if they were installed separately. This increased heat can reduce the wire's ampacity. Adjustment factors for the number of current carrying conductors are provided in NEC Table 310.15. B3. For example, if you have 7 to 9 current carrying conductors in a raceway, the adjustment factor would be 0.70. This means that you must multiply the allowable ampacity of the wire by 0.70 to determine its derated ampacity. It's important to note that these derating factors are cumulative. If you have both high ambient temperature and multiple current carrying conductors, you must apply both correction factors to determine the final derated ampacity. Ignoring derating requirements can lead to overheating, insulation damage, and potential fire hazards. It is essential to carefully consider all applicable derating factors when sizing wires for electrical installations. In addition to derating, it's also important to consider voltage drop when selecting wire sizes. Voltage drop is the reduction in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or fail to operate properly. The NEC recommends limiting voltage drop to no more than 3% for branch circuits and 5% for feeders. To calculate voltage drop, you can use the following formula: voltage drop equals 2 times K times I times D divided by Cm, where K is the direct current constant, which is approximately 12.9 ohms circular mils per foot for copper conductors, I is the current in amps, D is the one-way distance in feet, and Cm is the circular mil area of the conductor. The circular mil area of a conductor can be found in NEC Chapter 9, Table 8. Once you have calculated the voltage drop, you can compare it to the recommended limits. If the voltage drop exceeds these limits, you must increase the wire size to reduce the resistance and lower the voltage drop. Voltage drop is more pronounced over longer distances, so it's particularly important to consider when running long circuits. It's also important to consider the type of load being served. Motors and other inductive loads can cause significant voltage drop during startup. When sizing wires for these types of loads, it's essential to use a larger wire size to compensate for the inrush current. Proper wire sizing is crucial for ensuring the safe and reliable operation of electrical equipment. By considering ampacity, temperature ratings, derating, and voltage drop, you can select the appropriate wire size for any application. Always consult the NEC and other applicable codes and standards when making wiring decisions. Moreover, the type of insulation used on a wire plays a significant role in its overall performance and suitability for different applications. THHN insulation, which stands for thermoplastic high heat resistant nylon coated, is a common type of insulation used in building wiring. It offers excellent resistance to heat, moisture, and abrasion, making it suitable for both dry and damp locations. However, other types of insulation are available, each with its own unique characteristics and advantages. For example, THWN insulation, which stands for thermoplastic heat and water-resistant nylon coated, is similar to THHN but offers even better resistance to moisture. It is often used in wet locations or where condensation is likely to occur. THHW insulation, which stands for cross-linked polyethylene high heat resistant water resistant, is another popular choice for building wiring. It offers excellent resistance to heat, moisture, and chemicals, making it suitable for a wide range of applications. UF cable, which stands for underground feeder cable, is designed for direct burial in the ground. It has a tough, moisture-resistant outer jacket that protects the conductors from damage. When selecting a wire for a specific application, it's important to consider the environmental conditions and the type of load being served. Choose an insulation type that is appropriate for the location and that can withstand the expected temperature, moisture, and chemical exposure. Also, be sure to check the NEC and other applicable codes and standards for any specific requirements related to insulation types. Furthermore, the selection of appropriate wiring methods is as critical as choosing the right wire size and insulation. Wiring methods refer to how wires are installed and protected within a building or structure. The NEC outlines various approved wiring methods, each with its own set of requirements and limitations. One common wiring method is conduit, which involves enclosing wires in rigid metal conduit, electrical metallic tubing or EMT, or flexible metal conduit. Conduit provides excellent protection for wires against physical damage and moisture. It is often used in commercial and industrial buildings, as well as in residential applications where a high degree of protection is required. Another common wiring method is cable, which consists of two or more insulated conductors enclosed in a protective outer jacket. Types of cables include non-metallic or NM cable, armored or AC cable, and metal-clad or NC cable. NM cable is commonly used in residential wiring for branch circuits. AC cable is similar to NM cable but has a flexible metal armor that provides additional protection. NC cable is similar to AC cable but has a solid metal sheath that offers even greater protection. When selecting a wiring method, it's important to consider the environmental conditions, the type of building, and the applicable codes and standards. Choose a wiring method that provides adequate protection for the wires and that meets all safety requirements. Also, be sure to follow all installation instructions and use approved fittings and connectors. Moreover, grounding and bonding are essential components of a safe and effective electrical system. Grounding provides a path for fault current to flow back to the source, allowing overcurrent protective devices such as circuit breakers and fuses to trip and energize the circuit. Bonding connects all metal parts of the electrical system together, creating a low impedance path for fault current. Proper grounding and bonding help to prevent electrical shock hazards and minimize the risk of fire. The NEC outlines specific requirements for grounding and bonding, including the size and type of grounding conductors, the methods for connecting grounding electrodes, and the bonding of metal enclosures and equipment. It's important to follow these requirements carefully to ensure a safe and reliable electrical system. Also, be sure to test the grounding and bonding system after installation to verify its effectiveness. The NEC provides guidance on testing procedures and acceptable test results. Moreover, overcurrent protection is a critical safety feature that protects electrical circuits from overloads and short circuits. Overcurrent protective devices such as circuit breakers and fuses are designed to interrupt the flow of current when it exceeds a safe level. Circuit breakers are reusable devices that can be reset after tripping. Fuses are one-time devices that must be replaced after blowing. The NEC specifies the types and sizes of overcurrent protective devices that are required for different types of circuits and equipment. It's important to select the correct overcurrent protective device for each application to ensure adequate protection. Also, be sure to label all circuit breakers and fuses clearly to identify the circuits they protect. It is also important to ensure that overcurrent protection devices are properly maintained and tested regularly. Circuit breakers should be exercised periodically to ensure that they trip correctly. Fuses should be inspected for signs of damage or deterioration. Moreover, electrical safety is paramount when working with electricity. Electricity can be dangerous and even deadly if not handled properly. It's essential to follow all safety precautions and to use appropriate personal protective equipment or PPE. Always de-energize circuits before working on them. Use a voltage tester to verify that the circuit is de-energized. Wear appropriate PPE such as insulated gloves, safety glasses, and arc-rated clothing. Never work on electrical equipment in wet or damp conditions. Be aware of the potential hazards and take steps to mitigate them. If you are not qualified to perform electrical work, hire a licensed electrician. Electrical work should only be performed by qualified individuals who have the necessary training and experience. Moreover, regular electrical inspections are essential for maintaining a safe and reliable electrical system. Electrical inspections can identify potential problems before they become serious hazards. A qualified electrical inspector will examine the wiring, grounding, bonding, overcurrent protection, and other components of the electrical system. They will look for signs of damage, deterioration, or code violations. The inspector will provide a written report outlining any findings and recommendations. It's important to address any issues identified during the inspection promptly. Electrical inspections should be performed periodically, especially in older buildings or buildings with a history of electrical problems. The frequency of inspections will depend on the type of building and the applicable codes and standards. Moreover, understanding the NEC is crucial for anyone involved in electrical work. The NEC is a comprehensive set of standards that governs the safe installation and maintenance of electrical systems. It is updated every 3 years to reflect the latest technologies and best practices. The NEC covers a wide range of topics, including wiring methods, grounding, bonding, overcurrent protection, and equipment installation. It's important to be familiar with the NEC and to follow its requirements carefully. The NEC is available for purchase from the National Fire Protection Association or NFPA. It is also available online through various subscription services. Moreover, continuing education is essential for staying up to date on the latest electrical codes and technologies. The electrical industry is constantly evolving, with new products and techniques being developed all the time. Continuing education courses can help electricians and other electrical professionals stay abreast of these changes. These courses can cover a wide range of topics, including the NEC, electrical safety, and new technologies. Continuing education courses are often offered by trade schools, community colleges, and professional organizations. Many states require electricians to complete continuing education courses to maintain their licenses. By investing in continuing education, electrical professionals can enhance their skills and knowledge and provide better service to their customers. Furthermore, electrical troubleshooting is a critical skill for identifying and resolving electrical problems. Electrical troubleshooting involves systematically investigating a circuit or system to determine the cause of a malfunction. This process typically involves using a multimeter or other test equipment to measure voltage, current, and resistance. By analyzing these measurements, a technician can identify the faulty component or wiring. Electrical troubleshooting requires a thorough understanding of electrical circuits and components. It also requires patience, persistence, and a systematic approach. There are many resources available to help electricians and other electrical professionals improve their troubleshooting skills. These resources include textbooks, training courses, and online tutorials. Also, remember that electrical work can be dangerous. Always follow safety precautions and use appropriate personal protective equipment when troubleshooting electrical problems.